change gears a little bit now. So this, I think, is a new page in your comp book. Radiation and temperature. So what goes on with radiation and temperature? Well, something that's intriguing is if we were to measure the intensity of light, okay, so that's how bright the light is, through the spectrum now, for something that's emitting a temperature, a particular temperature. So if I have an object that is heated up to 6,000 Kelvin, pretty warm, okay, you would find, and you measured all of the different wavelengths of light. So this is a wavelength down here in micrometers. A little funny looking U, by the way, is a millionth of a meter, okay? Where a nanometer is a billionth of a meter. What you would find is they would give off different colors of light. But you would actually always find it so it makes this kind of curve thing. The top of the curve is the top temperature, and you can actually figure out if you know what that temperature is, and if you're at a colder temperature, colder doesn't seem that cold when it's 3,000 Kelvin, but if something's emitting light, usually it's quite warm, then you can find out some interesting things. And it is called Wien's law. Actually, it's Wien's law. Kind of a weird, got a W, I think it must be German or something. And he said, and if you don't have this in your notes, definitely should copy it down. The wavelength at which an object radiates most strongly is inversely proportional to the object's temperature. Now, now we're getting weird. That's kind of hard math, isn't it? Inversely means if one number goes up, the other number goes, well, down. Up, down, kind of a thing. So that's what inversely means. But we can also look at it as it's an equation, where the temperature is equal to this number, this constant, 3 times 10 to the 6th, and that's Kelvin per nanometer, divided by the maximum wavelength. So if you know what your maximum wavelength is, you can determine the temperature. So this lambda m, remember lambda is the symbol for wavelength, that's the wavelength in nanometers, and the temperature in Kelvin, and this is then what's called Wien's constant. So what do I mean, the maximum wavelength? Well, if we go back to our picture right here, so if my maximum wavelength right here is this number right here, whatever that happens to be, you could look at that up there. You could find that maximum wavelength. You can actually determine what the temperature is. And so we'll do a problem like that in just a minute. In fact, well, heck, let's do it now. Hey, what do you need to get out? That's right, your calculator. So I need to get my calculator out. So here's the question we want to ask. What is the temperature of the sun given that the maximum wavelength is 500 nanometers? Well, what's our equation again? T equals 3 times 10 to the 6th, so T is equal to 3.0 times 10 to the 6th Kelvin nanometers divided by lambda max. Well, all we have to do is plug in 500 nanometers into this equation. So I'm going to substitute in my numbers. Substitution is a good thing. 3.0 times 10 to the 6th Kelvin nanometers divided by 500 nanometers. What's going to happen is my nanometers are going to cancel, and I can then get the answer. So let's go over to the calculator, and I'm going to type in 3.0. And I'll do second function e. Remember, I do not say times 10. I do second function e for the times 10 to the 6th. And I'm just going to divide it by 500. And I get the number of, what do I get? I get 6,000. 6,000 Kelvin. So guess what the temperature on the surface of the sun is? That's right, it's 6,000 Kelvin. So if you were to then analyze any star, you could figure out what the temperature of that star is. You just have to find that maximum wavelength. You'd have to draw the chart like we have here for this one. So if I were to find a star, find that maximum wavelength for here. Actually, this has already told you that's 5,000, but you could do the math, find out what that maximum thing is, plug it into the equation, and you can determine what the temperature is. It's really not terribly difficult. It's a simple little equation that is right here. And here it is right here. In fact, I should turn the calculator off. This is the equation. So if you know what this equation is, you can actually find. And conversely, by the way, if you know the temperature of an object, you can find the maximum wavelength. And the last thing I want to talk about today is something called a black body. What's a black body? Okay, it's something that absorbs all the light falling on it. Okay, and that makes the radiation curve smooth. That radiation curve that we saw with the Wien's law, that's the curve we're talking about. Examples include the sun and the earth. So But interestingly enough, not everything works with Ven's law. You think that'd be great. Things that don't include Ven's law are things like fluorescent lights and neon lights. You see the picture here of the gal who's got a neon light on her bicycle. That'd be pretty cool. I knew somebody had one, like my cousin did. It was pretty cool when he would ride his bike in the dark. But anyways, they don't obey Ven's law for lots of reasons. And so black bodies are something that's studied in astronomy, because we can look in the sky and say that's a black body and that's not a black body. And there's interesting science around black bodies. I just want you to kind of know what they are as opposed to try and figure out that other stuff. That'll come later on when we learn about galaxy clusters and nebulas and things of that nature. Okay, so that concludes podcast 3.2, whatever it is. Was it 2? I think it's 2.